Hello everyone, I'm Haogu from Tsinghua University. I'm here to present a research work on behalf of my colleague Junyu. This is a collaborative work by Tsinghua University and Alibaba Group. This work focuses on log storage. As reported by Amazon Cloud Storage in this year, log storage has become one of the most popular services. According to Alibaba Cloud, the scale of logs can grow up to petabytes per day and must be stored for at least 180 days. Consequently, engineers and researchers have been striving to compress the log densely. However, how to execute aggregated analysis on large-scale compressed logs remain an open challenge. Pattern-based log compression is the state-of-the-art method today. This approach fully leverages the inner structure of logs. It first parses logs into structured output statements and variables like the timestamps, file paths, block numbers, and so on. It then extracts patterns for each type of variable, as shown here. These patterns can be used to reorganize variables into several fine-grained storage units, each compressed and decompressed independently. All compressed units, along with the mapping file and static content, form the compressed file. Queries use the mapping file, static content to filter units, decompressing only a small subset. Pattern-based log compression is used to compress large-scale logs in Alibaba Cloud. However, when executing aggregated analysis on these compressed logs, we face two fundamental challenges. First, in practice, large-scale logs are split into log blocks, leading to two pattern extract schemas. The first schema is global pattern-based schema. It extracts patterns from a sample of all log blocks and then uses these patterns to compress each log block. Another schema is local pattern-based schema. It executes the pattern extraction process on each log block and compresses logs accordingly. During aggregated analysis, a global description is crucial to aggregate specific variables within patterns. However, global descriptions often lack local precision, affecting pattern filtering efficiency. For example, global pattern BLK applies to all log blocks and supports aggregating on these variables. However, in some blocks, the first variable is actually a constant, so using local patterns can avoid decompressing unnecessary units. As for the second challenge, pattern-based log compression generates numerous units containing only numbers. We call them n units. Encoding n units as integer vectors can facilitate aggregation. For example, to execute this command, need to first filter with BLK3, then filter with length larger than 40, and finally calculate the largest length. The last two steps can be facilitated by encoding n units as integer vectors. However, since logs are text data, we have to support full text queries on these units. So, how to execute pre-suffix queries on numerical encoded units remain challenging. To address the dilemma between global and local extraction, we propose a two-phase pattern extraction approach. We decouple pattern components into sketch to local variables and specs, namely other details. We extract sketch globally and specs locally. Sketch provides a global description, and both sketch and specs filter units. The paper details how to decouple these components while maintaining filtering effectiveness equivalent to local patterns. To solve the second challenge, we propose to leverage SIMD to execute queries on n units. However, performing vectorized prefix queries is the most challenging part. We noticed vectorized prefix queries equal to check if the encoded numbers are within specific ranges. We call these ranges as the compare ranges. Compare range differs for each number and is challenging to be decided in a vectorized manner. However, by executing vector shifting operations, it's easy to decide the power of 2 range corresponding to each number. We call such a range as the squeezing range. So, what is the correlation between squeezing range and compare range? We prove in the paper, each squeezing range contains at most one compare range. Based on such a theory, we can get such a table showing the correlation between squeezing and compare range. The squeezing range can be decided by counting how many write shift times are needed to let a number become 0. We thus propose our vectorized prefix queries algorithm as follows. Given an n unit, we first execute vectorized right shifting until some vectors become 0. We can decide the corresponding compare range for these numbers according to the shifting counts and the table. The corresponding compare range can be loaded to the SIMD register using vectorized blending operations. We do the same thing continuously. If some shifting counts do not have a corresponding compare range, we just load an empty range. When all encoded numbers become 0, we get the compare range for each number. And finally, we can execute vectorized range query on these numbers. We implement and integrate all proposed techniques into a log storage system called LogCrisp. Its workflow is as follows. LogCrisp first extracts the global sketches based on a sample of all log blocks. It then extracts specs as well as all units for each log block. Each log block will be compressed as a zip file. Within the zip file, we have local specs as well as several units, mapping and static content. N units will be encoded as integer vectors to support vectorized aggregated analysis. We evaluate LogCrisp on Linux servers. We use 3 datasets. 2 of them are opened by previous works. The last one is a real-world production datasets used by Alibaba Cloud. We also evaluate LogCrisp on a 6 TB dataset to show its performance on large-scale logs. We compare with 2 baseline systems, CLP and LogRep. They are SOTA systems for global pattern-based method and local pattern-based method, respectively. We find LogCrisp can achieve the lowest analysis latency on all the datasets we tested. Its analysis latency is about 15 times lower than CLP and 4 times lower than LogRep. Since log storage is an art to strike a balance among analysis latency, ingestion speed, as well as compression ratio, we plot the results in a 3D radar figure. As for ingestion speed, global pattern-based method, namely CLP, is supposed to have the best result since it only needs to extract patterns for once. LogCrisp can outperform local pattern-based method by up to 2 times on open logs and 3 times on production logs. The ingestion speed of LogCrisp is comparable to global pattern-based method. It even outperforms it on 2 log types. As for the compression ratio, these 3 log storage methods show comparable results. LogCrisp achieves 89% and 97% of the highest compression ratio among all the systems on open and production dataset, respectively. We also evaluate the impact of 2-phase pattern extraction schema in respect to these 3 metrics. Compared with only extraction patterns globally, LogCrisp can improve the analysis performance significantly while keeping a high ingestion speed and compression ratio. Besides, we find by introducing vectorized queries, LogCrisp can execute vectorized pre-suffix queries with a lower latency than querying directly on string encoded data by up to 1.5 times. Now, let's conclude our paper. We try to answer the following question, namely, how to execute aggregated analysis on large-scale compressed logs. We face 2 fundamental challenges. One is between global description and local filtering effectiveness. Another is between numerical encoding and full-text query. We thus propose 2-phase pattern extraction schema to deliver global description and maintain the filtering effectiveness. And we propose a pre-suffix query algorithm to enable vectorized aggregated analysis on highly compressed logs for the first time. Finally, we implement, optimize, and evaluate a new log storage system named LogCrisp. Thanks for listening. If you have any questions, please contact my colleague Junyu by these emails or via Slack. Thank you.